So in the previous part we have seen the problem or the drawbacks of the hill climbing search. The drawback was the hill climbing search can get stuck at a local maximum value or a local optimum value, so which is not the best solution, and in that case we will have to settle for a solution which is not the best one. So in that case we need to modify the hill climbing search. So we are going to modify in two parts of the search. First, we're going to modify the choice of the neighbor that we're going to make, and we're going to modify the criteria for accepting a neighbor of the current state. So how do we actually do this? At first, we choose the neighbors randomly. We accept the neighbor if it is better than the current state, or we even accept the neighbor if it is not better than the current state with a fixed probability p. So how does this one help us to escape the local maxima? Let's say this is the local maxima, and whenever we were searching in the state space landscape, we are currently at the local maximum value. So when we are currently at the local maximum value, in the previous case we will keep looking for a better successor. Until we find out a better successor, we will not move. But unfortunately we can see that the successors that we have here are not better than the current state. So in that case, if we accept a neighbor, if it is not better than the current state with a fixed probability here, if we accept this neighbor, if we go from state 0 to state 1, we're accepting a neighbor which is not better, but we're accepting it with a fixed probability. And then again we're accepting another neighbor which is state 2, and which is not a better neighbor either, so we are even accepting it with a fixed probability. So when we've done that, we've already escaped the local maxima. So now we can go all the way up to the global maxima. So in that way, modifying the hill climbing search can help us to escape the local maxima. So let's look at the next slide. Here there are some slight problems with the modified hill climbing search. Here the problem is, at the first part of the search we're initializing with a random state, but at the end we're supposed to make better moves, but here we are allowing moves even if it is not better. So the chances of making a bad move is same all throughout the search. We don't want it. We want to reduce the number of bad moves. So, and we are ignoring the magnitude of improvement. That means we are not comparing whether the state is better or not. We're accepting whether it is better, or even we're accepting it if it is not. So to address these concerns, instead of using a fixed probability, we can accept a bad state with a probability that keep on decreasing. So at first when I accept a bad state, the probability will decrease. For the next bad state that I reach, the probability will increase further. So that means when the search progresses, the chances of making the bad moves reduces, since we're decreasing the probability more and more. Now we will look into variations of the hill climbing search. Many variants of the hill climbing search have been invented. The first one is stochastic hill climbing search. In the stochastic hill climbing search, it chooses at random from among the uphill moves. So the probability of selection can vary with the steepness of the uphill move. So this usually converges more slowly than the steepest ascent, but in some state space landscape it finds a better solution. And then the next variant is the first choice hill climbing search. It implements the stochastic hill climbing by generating successors randomly until a better state is generated than the current state. So we keep on looking, we keep on generating successors randomly until we generate a state which is better than the current one. So that is good strategy when state has many successors. Let's say we have thousands of successors. So in that case, this could be a good strategy. The hill climbing algorithms described so far, they are incomplete. So they often fail to find a goal when one exists. because they can get stuck at local maxima. Now let's look at another variant of hill climbing search, which is known as random restart hill climbing. So what it tries to do, it tries to avoid getting stuck in the local maxima. How does it perform that? So it adopts a well-known proverb, which is, if at first you don't succeed, try again. So that means it keeps on trying. So it conducts a series of hill climbing searches from the randomly generated initial states. It will stop when a goal is found. It is complete with a probability approaching 1. That means, for a trivial reason, that it will keep on restarting until it finds a solution. For the trivial reason, you can see that it will eventually generate goal state as the initial state. So if a hill climbing search has probability P of success, let's say the hill climbing search has a probability P of success. So that means the expected number of restart required is 1 over P. So students, that would be all for today's lecture, and we will look into the simulated annealing search in our next video lecture.